So here you are given a graph, and the question, the first part, part A, which node is visited right after visiting node F if we perform traversals on G starting from A based on the adjacency list above. So then this is the list. So if you want to know which one will be visited next, then we need to do the DFS and check that. So we are starting from A. So if you follow the ordering that is given in adjacency list, A will go on to B, B will go on to C, C to D, D to F, and F to C. But here, the F to C is C is already visited, so we don't continue. So instead, we roll back to D. D has no other neighbor, so D goes back to C. C goes back to B. Now B has two other neighbors, D and F, but both of them visited. So then we go back to A. Now at this point of time, A can then go on to the next neighbor, E. And E, in theory, has two neighbors, D and F, but both already visited. So we don't visit them again. So then we return back to A. A can go on to F, but F is already visited. So then we don't do it again, so it's all done, right? So then the DFS will be A, B, C, D, F, E. So then if the question is what node is visited right after F, then the answer is E, right? E is the one that follows F. Okay. Then the next part of the question says that invert the direction of one H and G so that we get a DAG, okay? Find a topological order in the resulting DAG. Okay, so then we need to know that one of them, so if we have to get a DAG before, that means before we get a DAG, it was a cycle, right? There was a cycle somewhere. So then we need to find out where is a cycle. Okay, so one way to do that is to try to visualize it. So let's try to do that. In this case, what we're going to do is to draw the graph. So we have A. So let's say. Okay, so let's see. A goes to D, E, and F. B goes to C, D, and F. C goes to D. D goes to F. E goes to D and F. And F goes to C, okay? Alright, so that's the graph, right? So we need to find a cycle here. Okay, so nothing is incoming into A, so A cannot be part of any cycle. Okay, so we can see whether there is any cycle involving B. So the resultant comes in from A, so it must involve A, but A, B. So if it's A, B, then it will be F, but F is not, okay, it's not a cycle there, right? Is C involved in a cycle here? Yes, right? So there is a, if you follow the outer lines here, there is a cycle. So for example here, okay, so let me double, okay, so F going to C, C going to D, D going to F. Now this is a cycle. And because it's a cycle, then it is not a DAG. So in that case, then we need to remove the cycle for us to have a DAG. Now, which cycle we are going to, which edge we're going to remove? Well, we can't remove, we are asked to invert, right? So we just need to change the direction. So in this case, one possibility is to invert this one, right? So FC becomes CF, right? So that is one of the possibilities. Now if we do that, then in that case, we are going to have C to F instead of F to C. And if we do that, then we will break the cycle, because there is no other cycle here. Okay, now, so if we break that, which means that the original graph here is going to change. It's not going to be the same as before, because then the C here is going to be removed, and instead we're going to put F here, because we are inverting it. So no more F to C, we have C to F. Then the topological ordering here. Well, we did DFS earlier. So A to B, B to C, C to D, D to F. F has no outgoing neighbors. So then upon return, F is going to go to the stack, followed by D, followed by C, followed by B. Now at this point of time, A can still go on to E. So upon return, E goes to the stack, and then A. So then we have A, E, B, C, D, F. That is one topological ordering. And if we check A, E, A, B, A, F, B to C, D, and F, C to D, and C to F, D to F, E to D, and E to F. Right, that's it, right? Everything is pointing forward. So that is one topological ordering. Okay?
So Prof, it doesn't matter which age you invert, right? It's just, as long as you invert one and it's not a cycle anymore, then it's fine.
Right, yeah. So here you just need to invert one. So if you invert a different one, and if there is no other cycle, then you should get a different topological ordering. Now in reality, of course, you can't just anyhow invert your edges, right? I mean, that's there is a meaning behind the graph. So in that case, that means that there is probably something wrong in the way that the graph is constructed, because otherwise, if it is supposed to indicate the precedence or the prerequisite relationship, then there shouldn't be a cycle in the first place.
Is there another way to find out, other than traversal, getting the inversing of edges?
So in the inversing of the edges?
Yeah, it's like, instead of drawing it out, is there another way to like induce which one to invert?
Do you have another way? What is your way then? Do you want to share your solutions?
No, I'm just asking, because like, I also draw it out, but is there another way?
Okay. There are algorithms to find cycles on the graph. So then you will output the cycles, and once you get the cycles, you just try to break it. So once you invert, you check, you run the algorithm to see whether or not there is a cycle. Okay. Now, the key points of the graph method, we didn't go very much into graph actually. So there are a lot of things that are useful that you can do with the graph. So far I think in the course we can only talk about the graph structure, the traversal, as well as just an example, which in this case is topological ordering. They are, if you are curious, you can of course go into, look at different kind of graph algorithms. One kind of graph algorithms essentially is, like in this case is the ordering. Another kind is the shortest path algorithms. Those are the ones that are trying to find out in how many ways can you go from one part of the graph to another part of the graph. Can you go there in the shortest possible way? And of course, we have not touched a lot in terms of the weights of the edges. Once we do the edge weights, then there are problems. Like for example, there is a problem called the maximum flow problem. That's the idea of which path do you go from one part of the graph to another to ensure maximum flow of, think of it like a pipe, like different sizes and so on.